So again, thank you for that kind introduction, and I really want to thank the working party for the invitation to speak to you today. For those that were hoping for Jean-Paul, I apologize. I'm not going to be able to be anywhere close to his level of presentation skills, but nonetheless, I do hope that you'll find that what I'm talking about today to be interesting and hopefully motivating. Today I'll talk about, as Brian said, utilization of inline wet milling for particle size control during a continuous crystallization. I will say when we started this work, it seemed like it was such an easy concept. And then as I will point out, it turned out to have some challenges that were pretty exciting to overcome. This project that I will discuss is a very real project. And you can tell by the large number of collaborators on this work that there was a lot going on. So this was part of a multi-step, fully continuous drug substance process, which involved, I believe, 3 different chemical transformations, a couple of different separations, liquid-liquid extraction, distillation, concentration, you name it. And then at the tail end was the crystallization and isolation of the API. I want to call out one particular colleague in particular, and that's Václav Svoboda. Václav really should be giving this talk today. He did the lion's share of the experimental work that I'll be discussing. So appreciate and acknowledge all the efforts that he provided to this work. And then my collaborators at PSE who helped to with the modeling aspects that I will discuss. So let me dive in and give you just a bit of background of the project. As those of you are aware, if you've been following the pharma industry in the last 5 years or so, there's been a great interest in continuous manufacture. And for us, there's been a great interest in continuous manufacture of drug substances for molecules that are quite small in volume or projected volume at time of commercialization, such that these processes can fit into a standard laboratory fume hood. And in fact, that's garnered so much interest at Lilly that we've made a major investment in our manufacturing organization in Ireland to afford such technology. So this was one of the first projects that was to run in that facility. It was for an API that, like I said, was a fully continuous multi-step synthesis. The API itself was dissolution rate limited. So in pharma speak, that means that if the particle size was too large, then the drug wouldn't be fully dissolved and absorbed in the body when taken. And so we needed to keep the particle size, the D90 or X90 quantile, below 250 microns. We also had a lower limit that we had to stay above. That was 130 microns from a processability perspective downstream in our tableting operations. So a pretty broad window that one should be able to comfortably manufacture within. Our desire for continuous crystallization, and as for any API crystallizations, is to control those physical properties in the crystallization process itself. But in this particular case, we found that growth dominated nucleation, and that the smallest size we could achieve without other processing issues in the crystallization was around 450 microns. And typically where we centered that at was closer to 500 or 600 microns. Those other concerns were around fouling. If we ran with too high of a supersaturation, fouling was a major issue with this particular system. And so we gave up on our attempts to try to control the particle size just through control of our crystallization conditions, resonance time, antisolvent addition, number of MSMPRs, and instead we controlled it with a batch terminal milling step. So we would collect up product as a slurry, and then we would take that and run that through a long batch wet milling operation to reduce the size down. And because of time, we had to make material this way to get into clinical trials on a couple of occasions. But the goal for commercialization was to remove this terminal batch milling step, but instead intensify the process and utilize an in situ wet mill with the existing continuous process. So the system that had been developed is shown schematically here. The crystallization was optimized to work in 3 MSMPRs. The system does start with product that comes from this long cascade of reactors, CSTRs, PFRs, and that product that can either be fed through the continuous process itself or collected in solution and fed into the crystallization process enters. It enters as what we call a crude API solution that's somewhat dilute in THF water, and it goes through an evaporator, a continuous evaporator, to remove the water, concentrate in THF, and then get the final concentration into a 25 weight % API solution. It then feeds our continuous crystallizer. It is supersaturated at room temperature under these conditions. So to avoid crystallization in the feed system, we do feed that hot. So we feed that above 60 degrees, around 70 degrees, into our cascade of crystallizers. And once it enters the cascade, it's combined with antisolvent in the first crystallizer, additional antisolvent in the second, and then the third is there to provide additional growth. Temperature is cascaded down from, like I said, the inlet of around 70 to 40 in the first, 30 in the second, and 10 degrees in the third. The product then is isolated in one of 2 filters that alternate in sort of a duty fill empty cycle. The filtration was important. We had an impurity that was extremely insoluble, and it was kinetically rejected. So what I mean by that is it was above its solubility limit at the isolation conditions, but it doesn't crystallize readily. If you allow it to sit for some period of times, it will spontaneously nucleate. But if we had a good filtration followed by a quick wash, we could remove that mother liquor, remove the saturated impurity with the mother liquor, and control that impurity down to almost non-detect levels. So the way that the cascade worked is we would take a segment of slurry, apply it to the filter, and then we would follow that immediately with a wash, and then again periodically take a segment of slurry, filter it, and then immediately wash it. The transfers, I should mention, from one crystallizer to the next, because of the scale that we operate at, are periodic in nature. So once every 20 minutes, we have a transfer from the third crystallizer to the filter, and then the second to the third, and the first to the second. And we have continuous feed of antisolvent and periodic transfer of solute in solution to the first MSMPR to avoid fouling at the inlet. And then, like I said, to achieve particle size, we took a slurry off the filter, we re-slurried off this filter, transferred it to a large batch vessel, and then in recycle mode, once we had a full batch vessel, milled that in recycle mode down to the target size of 130 to 250 microns. So you can see it's not optimal in the sense that we have this large batch operation at the tail end of a fully continuous operation. So our goal here, and what I'll be discussing today, is the placement and utilization operational conditions best to run an in-process wet mill. And so the first question we had is, where is best to place it? Is it in the first crystallizer, the second, or the third? And then secondary to that is what would be the optimal operating conditions to achieve our desired particle size. Of course, we had to do this and maintain the same level of impurity rejection or improve upon it. We also wanted to maintain or improve on yield, as well as decrease or remain the same with the fouling conditions. Like I said, this system was quite prone to fouling, so that was one item of concern. So I touched upon this in the intro. Some of the benefits of integrating the mill are really to eliminate this batch out process from a fully continuous interface. And then also that allows for a much smaller equipment footprint that reduces our overall cycle time of the process. It also avoids a couple of additional unit operations that you might not think of, and that's this re-slurry operation off the filter and additional filtration step. And the last benefit is we expected that we would see an improvement in the particle size distribution because we'd have fewer fines in the final product. For those unfamiliar with a wet mill, in other industries, this is called a high shear mixer, and that's because that's what it's designed to do. We utilize it though as a wet mill for particulate systems. It's a rotor stator geometry, so it involves a series of teeth that form the stator. They're stationary, as the name would imply, and then within that is an impeller or a rotator that also has a series of teeth that rotates at very high speeds and very tight clearances, a half millimeter gap. And then material flows through the teeth of the rotor and the stator through this high shear zone, and that high shear and then collisions with the rotor and the particle is what decreases the particle size. Some of the variables that one has in utilizing these wet mills are the tip speed at which it's operated at, the residence time or the number of turnovers one has through the mill, and then where one would place that within the cascade of MSMPRs. There are different geometries that are offered. So at the scale that we were working at in the laboratory, which is a small immersion mill, it's an IKA T25 mill is the one we use at this scale. We had the option of either using a fine generator or a coarse generator. At larger scales, this manufacturer does offer additional elements so that you can kind of span to other regions, but at this scale, this is all we had to offer. The crystallizers I should mention, I apologize I failed to, were 100 milliliters roughly working volume, about 150 milliliter total volume, and then in the end we ended up utilizing a 300 milliliter vessel. So you can tell it's quite small, laboratory scale, and this was about a 10th scale of what we expected commercial production to be. So the way that we approach this problem is the way that we have tried to approach all of our continuous crystallizations, and that's through a combined experimental and modeling approach. We found if you jump in and just start doing continuous crystallizations without an understanding of the kinetics of your crystallization, you can really chase your tail for quite some time. So instead what we do is we perform a series of laboratory experiments to ascertain kinetics in sort of a reaction engineering type way. We then utilize that with appropriate model discrimination to build an appropriate crystallization model. And then once we have that, we can then in situ or in silico optimize that process to understand where our optimal starting point should be when we go into the laboratory and run our first continuous crystallization experiments. And then based upon the parity that we see between the predicted results and the experimental results from that experiment, we determine if we need to further refine this model or not, or if we can use it as is. Adding a wet mill to the process requires an understanding of the kinetics of the breakage that we'd seen in that wet mill, and I'll talk a bit about that in a moment. This approach we found through time really minimizes the amount of material that we need. And where we're at in early pharma development, material is scarce. So a kilo of API may be a huge luxury, and we may instead have a couple of 100 grams. And so doing large scale, even large scale at 100 milliliter scale, continuous runs does consume a large amount of material, especially if you need to get to steady state. So we'd like to minimize that as much as possible. It also reduces our experimentation and development time, and it improves our knowledge of the process. It allows us a model that we can both interpolate within the process space was examined as well as extrapolate to some extent. Hopefully everyone's familiar with the population balance model. It's essentially a mass balance over the solute phase as well as a population balance model for the solid phase. We utilize a one-dimensional model. Growth and nucleation are shown here. So we use a secondary nucleation term that has in it a proportionality to the energy dissipation in the crystallizer. And then we need to parameterize that and determine these parameters that are shown in red. And we do that through these series of batch experiments. The desupersaturation experiments are very well spelled out in this reference. Essentially, you need to have knowledge of your solubility curve, here shown as a function of of temperature and concentration on the y-axis. So if we're above this curve, as shown by this point, we're supersaturated. So we would establish a level of supersaturation. We would then seed that to kick off crystallization. And we'd hold it under isothermal conditions, and then we monitor the rate of decay in supersaturation by IR, online IR, as well as we can monitor the evolution of particle size by FBRM. And then at the end of that, once we hit equilibrium, we can take a sample for offline particle size analysis. We can heat that back up, we can dilute it and dissolve a material again, and then seed at a lower level of supersaturation, and repeat this over a number of different temperatures and levels of supersaturation. And then from that large body of data, we can bring that into our population balance model, and then we can do the parameter estimation for the unknowns. And from that, then we now have a recreation of those experiments, and we've determined our kinetic parameters that allow us to then go through this cycle of now utilizing that parameterized model to determine what our crystallization kinetics conditions need to be to go into the laboratory. We started with that as a known, and what we didn't know is how to implement the mill, so we needed to extend that population balance model with the addition of a milling model. So for that, we utilized, we examined a number of different breakage models. The one that we found that worked in particular was one by Austin, published in '76. Population balance model for breakage includes both the birth term, that's particles of a given size band, as well as the death term as you're breaking those particles. In order to close that, you need a breakage kernel, and then you also need the selection function. So we then run a number of experiments that I'll discuss in a couple slides that we then are able to determine under a given set of conditions what the selection function is, as well as that breakage kernel. And then we have to correlate that to the equipment that we're using. These terms tell you nothing about your equipment conditions, so we then correlate that selection function to the conditions that one would use on the equipment. And so for a rotor stator mill, that can either be the shear frequency, how many events, how many collision events, if you will, does a particle experience through the rotor and stator. And that's shown here by the number of rotor teeth and stator teeth. The product of that times the rotation rate then gives you the shear frequency. The other way that we've seen good correlation is with shear number, and that's the shear frequency times the tip speed. So we evaluated both of those. These are both from the literature. So we didn't invent this, but we utilized what had been done. So to isolate the breakage, it's quite simple. We created a slurry in our vessel. We had the immersion mill in it. We ran under conditions where there were no crystallization was not occurring, so no nucleation or growth. And we then start the experiment by turning on the mill and monitoring the size evolution with time. And this gives you an idea of what this looks like. So here we start out with unmilled slurry, and we start the mill up at a low rate, about 15 meters per second tip speed, and we monitor that evolution of size with time. And then we do a step change in the tip speed to about 30 meters per second, monitor that with time, etc. You can also do it at lower rates, and then from this data, we can bring that back into our population balance model now with our kernel and model built in for milling, and parameterize those values. And then from that, now we have a full model of that describes both crystallization and milling. And now we can ask this question in silico: where is the best place to place this mill? Is it in the first crystallizer or the last? I don't show the results from that, but what we found in that modeling work is the best place to place the mill is indeed in the first crystallizer. It provided for a tighter particle size distribution by placing it there. So with that knowledge in hand, we then modified the experimental setup and placed the wet mill in the first crystallizer as shown in this picture. Schematic, what you're seeing in the picture makes it a little clearer. So we have our feed system of our concentrated API in solution. This is contained all within a hot box, or a box where the temperature of everything in that is maintained at 70 degrees. So there's no chance of any precipitation occurring in the lines. You can see that the lines are quite small at the scale. So it's very easy to have a cold spot, and by having all that in a hot box, we eliminate that. That's transferred then to the first of 3 MSMPRs. I mentioned this is done periodically. We do that from the third to the filter through trapping vacuum in an intermediate vessel. We then open that vacuum up to the third MSMPR, and we aspirate slurry from the third SMPR into this transfer zone. Once that's complete, we've got the level down that's controlled by a dip tube, which we're transferring through. We then pressurize this vessel and push that over to our filter. We then use trap vacuum in this vessel to pull slurry from vessel 2 to 3, and then we use a bit of overpressure to move from 1 to 2. And we do this periodically, and in this case, it was every 20 minutes we would initiate this transfer sequence. So with that description of our system and a little bit of background, we did the first experiment. The model predicted that we should achieve a size of around 100 microns. We're a little disappointed by that, and that's running at the lowest conditions. Disappointed because if you remember, that's below our target size, but we do know that, you know, models are never 100% accurate. So we went to the laboratory and we ran, and we achieved 90 microns. So we had good parity, so that was very positive between the model and what we saw in the experiment. We also did realize a very tight particle size distribution coming out the product. So this is out of the first MSMPR, and then the red is out of the third, and you can see that it is a nice tight distribution with a very small shoulder on the fine side. Although to do this, we had to run at the lowest conditions possible, so the lowest tip speed with the coarsest dispersing element. And so we didn't achieve our goal of above 130, but below 250. But we did see, like I said, pretty good parity with the model. This digs into that a bit more. So if we look at the parity between MSMPR1 and then what was predicted, we see agreement within 20 microns, a little better agreement in MSMPR2, and off by about 10 microns, as I mentioned, in MSMPR3. The prediction on concentration is shown here, so a little off on MSMPR1, but nonetheless quite close. And certainly the model is quite directional. But at this point, we couldn't rely on the model anymore, because the model didn't allow for some of the iterations that I will go into next that we started to utilize to get to target. So we were stuck when we got to this point as to what to do next. And so one item that we discussed was we could reduce the mill even further. We could modify it to operate at tip speeds lower than what the manufacturer has designed it to do. We could modify the rotor stator by changing the gap thickness or removing teeth. And we did these, and neither one produced results that helped, so I won't discuss those. The other is to utilize an intermediate operation. So what I mean by that is, like I said, every 20 minutes we cycled slurry from one vessel to the next. And so within that cycle, we thought if we turned the mill on and operated it for some period of time and then turned it back off, maybe that would be a way to achieve size, somewhere in between no mill, if you will, in which we get a product of 600 microns or so, and continuous milling, which got us down to less than 100 microns. That did pose one challenge, because we were using the wet mill also as the agitator, and so we had to decouple the agitation from the milling, which meant we had to go to a larger vessel. So you can see this is a 300 milliliter vessel. It's quite full with the dispersing element in it, as well as the impeller, but it does fit. It did not fit in the 100 milliliter vessel. And then the intermittent mill was run by flipping the switch on for a minute or some period of time, and then off for the rest of that period. And so the sequence of operations then that we utilized was to transfer slurry between MSMPRs and the filter. And once that transfer was complete, then mill the contents of MSMPR1 for a period of time, and then add a portion of fresh feed to that, and then wait for the rest of that period of the cycle, and then repeat that over the course of the continuous run. This is where I really have to then acknowledge Václav, because that first proof of concept run was run over 8 hours, and he was the manual control for the mill. So every 20 minutes, he would flip the mill on for a minute, and then at the end of that minute, he would flip it back off, and he did this for an 8-hour day. How he had lunch or anything else during the day is a bit unknown to me, but he accomplished it, and it actually worked out amazingly well. So we weren't at steady state at the end of 8 hours, we knew that, but it did directionally tell us where we're going. And we saw that coming out of the first MSMPR, we were hovering around 190 microns, and coming out of the third, we were around 220 microns. And so we were almost spot on where we wanted to be, which was really phenomenal given given that 1 minute wasn't totally chosen by random, but nonetheless, we could not utilize our model for any sort of prediction in this case because we didn't have this periodicity built into the modeling software. So we then next went into a demonstration run for 30 hours of operation. This is when Václav said, no way am I going to sit there for 30 minutes and turn the mill off. Actually, he didn't say that, but I'm sure he thought it. But instead what he did is he automated it to where an actuator was used to flip the mill on and off for 60 seconds or some period of time over a given period. And so in this case, we did that 1 minute of milling every 20 minutes, and you can see the results coming out. So the first MSMPR, 200 microns, the second 270, and the last 280. So we're a little above target. So we ran it again, another experiment. We extended the periodicity of the milling to now 2 minutes every 20 minutes. And you can see we're right where we wanted to be, 185 microns. Just an absolutely beautiful result. So what looks like 3 experiments we got to target, it was really a bit more than that. But nonetheless, I think in the span of about 3 months, Václav was able to go from nothing to controlling in our range. And a lot of that time was also spent with the equipment configuration. So really shows the power of the work that he did. So the next step was then to work not with recrystallized material, but with reaction feed. The reaction feed comes in with a whole slew of impurities that can have an effect on the growth of the crystallization. We also wanted to test the effect of the mill on impurity rejection, and we wanted to see the impact over very long runs of what the fouling might look like, as well as if we step the milling interval, the duration, how that can change the size with time. So we did a 70-hour run, and we split that into 3 different milling conditions. One with a 2-minute milling cycle, one with 1 minute, and then one with 30 seconds to see the effect that time has on the final particle size. And then we also looked at impurity rejection, as I mentioned. What we found is we had very comparable yield to what we'd seen previously. And we were able to nicely almost dial in the particle size. And so here you can see what that distribution looks like. Again, it's quite tight relative to what we'd seen, and we're able to control to 140 microns in this first case. So it is smaller when we use the reaction feed versus recrystallized material, and that's consistent with what we'd seen previously. The 1 minute periodicity were much closer to target, around 170, and the 30 seconds, 220. So somewhere in that 1 minute to 30 second periodicity of running the mill every 20 minutes gives us right where we want to be. As I mentioned, fouling was a concern, and so using the crude material, we're able to see the impact of fouling. There's a little bit of a ring you could see at the top of the first MSMPR at the end of the run, but the other vessels are quite clear, and this really compares equally, if not better, to than what we had seen when running this process without the mill. And if we compare the particle size to kind of our reference, which was the continuous crystallization before milling, again, 600 plus microns. After this batch slurry milling, we are in the 200 micron range, but you can see a very big span, very broad distribution. And if we compare that to what we saw coming out of this in situ periodic milling case, 200 microns, very tight span, 1.3 formulation group, loves material that looks like this. So it was a huge win. Microscopy supports that as well. You can see very nice, well-defined crystals either by SEM or optical microscopy. Whereas if we look at the material that came out of the batch milling operation, many more fines and much broader distribution. So let me start to wrap up here and offer some parting thoughts. So for this particular work, we had a system where we were growth dominated and we're not able to achieve our target particle size. So there's a publication of a couple of years ago that a colleague of mine, Thomas Vetter, in collaboration with myself and Mike Doherty did, where he discussed attainable regions for a given crystallization system under different configurations, different number of MSMPRs. And that work found, this is for a different system, this is paracetamol, found that there's a region of which you can achieve particle size, and then there's another region where you can't. And so in this particular case, we were wanting to operate in a region down here below our attainable region. And we needed to shift that attainable region. And utilization of a wet mill allows one to negate this attainable region, or broaden it, if you will, and allows for another attainable region. But utilizing continuous milling moved that region now to another space. And unfortunately, we wanted to be in a space that was in between. So by utilizing intermittent milling operation at a periodicity that didn't interfere with our overall process dynamics, did provide the ability to bridge this gap. It also provided the advantage that we had much narrower distribution in particle size in comparison to doing a post continuous run batch milling operation. And while we haven't determined this yet, we do think that this is more robust to develop and scale up versus the alternative. I didn't talk about it much, but we have found that for systems like this that are very fast growing and slow to nucleate, that fouling is an issue. And one way to mitigate that is through avoiding high levels of supersaturation. We did see evidence that by utilizing the mill in the first MSMPR, most likely by providing more nuclei, if you will, more surface area to grow upon, we did see indications that fouling was improved and decreased. Some other considerations that I think are best practices when developing a continuous crystallization are as follows. So size control, we found, can be a real challenge, especially for these systems where growth dominates nucleation and you just can't get to your desired size through changing your process parameters. And if one doesn't understand the growth and nucleation kinetics well, one can really spend a lot of time doing experiment after experiment to try to drive nucleation and drive particle size down. Utilizing a crystallization model, a population balance model, is very helpful, I think, to provide directional guidance as to how best to manipulate those process variables. When you have 3 MSMPRs in series for a thermal and anti-solvent crystallization, your degrees of freedom are very large. And to understand the interplay in this highly nonlinear system experimentally is a very long and tedious and frustrating process that is overcome by utilization of population balance models. And I think they really do speed your process development time. They're not the panacea. They aren't perfect in prediction. As you saw, that we did not have great parity, but we had good parity that allowed us to get to desired endpoint very quickly. one can get to those needed kinetics through small batch experiments to ascertain your growth and nucleation kinetics and separate those from some of the other phenomena that occur. And then you can use that model then in process optimization and conceptual design. And that conceptual design phase, I think, is an important phase that as engineers, chemical engineers, we utilize on a regular basis to get to a desired endpoint much faster. So let me finish here where I started and thank again my collaborators. Especially would like to thank Václav for all the work that he did in developing this and giving me a lot of great information to talk to you about today. And thank the others that were not co-authors, but also instrumental in the lab to bring forward the information I showed now. And I'd be happy to open up the floor for questions.
Thank you, Chris. That was a fascinating presentation. And we do have a number of questions. One that arises is, maybe if you could comment in general on the applicability of your batch kinetics to MSMPRs. So you're collecting kinetics under one condition and how consistent they are when you start looking at the MSMPRs.
So Brian, that's a great question. And it's a question that we're asked a lot. So for some systems, that work that's done at batch gives us very good parity to what we then see when we go in to run our experiments. And when we start to look at this loop that I showed a couple of times, and nightmare. Okay, so when we get to this point where we now compare that first experimental result to the model results, and we ask the question, do we need to refine our kinetic parameters? In some cases, the parity is very close, probably with an experimental error. That's probably 50% of the time, I would say, on average. But at times, you do see some discrepancy. And so in that case, we do have to refine the model. Oftentimes, I will admit, the model, if you think the model is going to give you enough fidelity that you're going to say, I want 105 microns, and my model says this gives me 105 microns, and you run that experiment, you're not going to get 105 microns. The fidelity is just not there. And we've heard enough talks this week, very fine talks. Heiko's talk yesterday was good, that talks about the negative effects of using single dimensions for measuring size, as well as for the modeling. And I think that's part of the reason why these models fail. Is it because we've measured the kinetics in batch and we're applying it continuous? That could be part of it too. We do try to mimic the fluid mechanics between the two so that batch experiment is in a vessel that's geometrically similar to what we're using for the continuous run. And we think that also helps, but it's a good question.
And maybe related to that, and you touched on it there with some of the presentations earlier in the week, there are examples of continuous crystallizers delivering perhaps different particle shapes to batch systems. And have you looked at all at maybe integrating more than one-dimensional modeling into the system?
Yeah, that's another great question. So I will say you must be reading our wish list, because that's definitely on there. But that's one aspect of industrial research, is to really evaluate and develop that technology is outside of the realms of our development goals, if you will. That said, though, we are interested, and we have collaborated in areas. We have strong interest in both multidimensional measurement techniques as well as multidimensional modeling techniques. And it's a little bit of chicken and egg as we've started down these conversations. If we talk to the modeling group, they'll say, well, you need the measuring techniques so that you can parameterize the models. As we talk to the measurement groups, they're like, well, don't you need a model that you can then put these measurements into? So we really need both. And I think it's an opportunity for a lot of advancement in the area. And that's why I'm so excited to see the work that, like Heiko and others have talked about this week, to really advance in those areas.
And a question that has come up as well is a perennial one about when you are looking at your modeling, how you might utilize FBRM data, offline PSD data, and how you try to in some way reconcile the differences.
Yeah, so that's a great question. So, I showed that we had the FBRM probe when we do these kinetic desupersaturation experiments. Oftentimes we'll have an FBRM probe in the system. We have not used the FBRM data to parameterize our model for particle size. What we use that FBRM probe for is we find that it's a little more sensitive to ensuring that we're at equilibrium or at steady state, if you will, than what the concentration measurement shows. But we have relied primarily on that offline particle size measurement by laser diffraction. We've done that for two reasons. One, our overall metric, if you will, our release specification is on particle size as measured by laser diffraction. So we have kind of a one-to-one correlation, if you will, with model prediction and what our refereed result is going to be. But the other is, and Vasilov did this as part of this work, was trying to utilize the FBRM data as a surrogate for that offline measurement. And, various institutions have come up with ways to correlate the two. And we found sort of mixed results on that correlation and the applicability. And so as a company, it's not something that we've spent much time using the FBRM data in a way, anything that's more than qualitative or quasi-quantitative, but we do know that others have, just not the experience that we've had to date.
Maybe just there was one or two questions on the integration of the milling then. And could you maybe just comment, presumably you may have achieved the same particle size if you integrated the wet milling with a batch crystallizer. So I'm just wondering about the driver to implement the system continuously.
Yeah, so that's a great point. So this process early in its development was done fully batch. So the synthesis was batch, and then the crystallization was batch. This is one case where continuous offered a huge advantage over batch crystallization, and that's because of this impurity I spoke of. So we had an impurity that's extremely insoluble, and it was present in fairly low concentrations, I believe about 0.4 weight percent relative to the API. We needed to control it down to below 0.1 weight percent. And its solubility was such that almost all of it would want to end up in the API and under the conditions we were isolating at. When we did the batch crystallization, for many batches, we never saw the impurity in the API. And then we started to see it show up as we went up in scale. And that's what gave us an indication that we were kinetically rejecting this impurity. And that's one disadvantage as you go up in scale with batch. Time elongates. Time on your filter elongates, the time between washes elongates. And so that propensity for that impurity to now nucleate and crystallize in your filter or in your crystallization vessel increases dramatically, right? And so that's why we started seeing it. But when we run continuous, because the time constant, if you will, that continuous operation was smaller than that nucleation time constant, if you think about it from a time perspective, we were able to kinetically reject it. So as long as we kept the process going and we then filtered off the mother liquor and then washed it, and we did that in a very robust manner, we're able to control that impurity. And so that was a huge driver to run this process continuously versus batch. The other driver is because the synthesis up front of this was fully continuous. And so because all of that was continuous, it just makes sense to keep a small footprint and to work within the confines of our small volume continuous plant that we built was to have the crystallization fully continuous. And so that really was the driver to not batch out the crystallization and then wet mill it as suggested, or do what we had done, and that is batch out the milling aspect of it as was run prior to this work.
And again, there's a lot of questions coming in, but I'm conscious of time. But again, on the intermittent wet milling, this may seem like a glib one, but in terms of the mechanism, do you think is 2 minutes milling every 20 minutes the same as 1 minute every 10 minutes?
Oh my gosh.
Have you thought, in other words, have you thought about the mechanism and how you might look at integrating that into the modeling?
Yeah, my flippant answer is we have a poor internet connection. I don't think I heard the question, but I don't think I can rely on that answer. So at the time, we did not have a model to look at that. That is an excellent question. Since then, I've worked with the group at PSC, Niall, Felipe, and Samoa, and we have developed they have developed that intermittent model. And so that is something that definitely would be worth investigating. But no, we've not. I've not looked at that. My guess is that you will end up with a bit broader distribution, but that's only a hunch. Okay.
Look, Chris, again, there's a lot more questions, but I'm afraid we do have to call halt. But again, just thank you again. That's been a fascinating talk, and I guess the number of questions indicate the interest in the audience. But thanks very much for joining us.
Thanks, Brian. Thanks, everyone.
So if you can stop sharing your screen, if that's okay, and I'm going to ask our next speaker, Alison Lewis,